Okay, welcome back. When we left off last time, I had asked you to answer these questions. So we're going to go over them now. How are temperature and heat related? Well, they both are measuring the motion of the particles in a substance. Okay? Temperature is the average energy of those particles. So it doesn't depend on how much of it there is. It's the average thermal energy, the average motion of the particles. So the more heat, the higher the average. So, if we raise the temperature of water from room temperature to boiling, the particles are going to have more thermal energy. They're going to have a higher average. Okay? So total increases is the average increases. Heat or thermal energy is the total energy of all the particles, atoms, and molecules of a substance. So, like I just said, if we increase the temperature of one sample of water from room temperature to boiling, the total energy of the particles increased because they all have more energy when they got to boiling. But if we had two pans of water that were boiling, and one of them was a great big large kettle of water, because it has more particles in it, even though they both have the same average because they're both at boiling, the one with a large amount of water would have a greater total, which is the example that we went over last time. What are two ways to increase thermal energy? Well, it's these two right here. We can add more heat to a substance, or we can increase the mass of the substance. So it increases as temperature increases, it increases as mass increases. When is temperature change positive? Okay, when heat flows into a substance. So remember I said heat always flows from high to low. So in the summertime, it's low temperature inside the house and it's warm outside the house. So the heat is flowing from outside to inside. So it would be correct to say that you want to keep the heat out, not keep the cold in. Okay, the cold doesn't have energy. It doesn't want to go anywhere. Okay, the particles outside the house have a lot of energy. They want to transfer their energy into the house. How does heat move? It always moves from high to low or hot to cold. When is temperature change negative? It's when the heat flows out of a substance. So in the wintertime, when a house is warm and it's cold outside, when the heat flows out of the house to the outside, the temperature change is negative. Notice how both of these say the heat flows. That's because it's heat. It's moving from hot to cold. Now, you should kind of remember from elementary school that there's three ways that thermal energy can transfer: conduction, convection, and radiation. We're going to take a look at each of those now. The first transfer of heat is conduction. It's the transfer of thermal energy through matter by the direct contact of the particles. Direct contact means they have to be touching. That's the direct contact part. Kinetic energy is transferred as the particles collide or bump into each other. So when you start heating something, right near the heat, the particles start to move faster, and then it bumps into the one next to it, and it keeps transferring the energy along. So in this example, it shows the frying pan is getting heat here. As the particles get heat near the bottom of the handle, it moves up the handle as they transfer energy. In this example, the particles next to the flame start gaining energy and they're bumping into the ones, and the heat is moving along through the air as the particles transfer energy. So again, here they're moving faster and they're transferring. These particles over here are still moving slow. They'll start moving faster after the heated particles bump into them. So one more time, just watch. Particles are gaining energy as the heat is bumping in, as the heat is being transferred from particle to particle. The next way heat is transferred is convection. And it says convection is the transfer of thermal energy by the motion of heated particles in a fluid, which, remember, is a liquid or a gas. Convection currents transfer heat from warmer to cooler parts of a fluid. Okay, now remember, kinetic theory again. As you heat a substance, the particles move faster and faster. As they move faster and faster, they spread out and take up more space. As they take up more space, they become less dense. Remember, density is mass divided by volume. if the mass doesn't increase, but the volume increases, then they're going to become less dense. As they become less dense, they rise. Okay, so the warm air rises because it becomes less dense. Now, if the air just rises and nothing comes in to replace it, there'd like be no air down at the bottom. That's not going to happen. Cold air is going to come in to replace that warm air from someplace. Also, as it's rising, okay, the air is going to start cooling and it loses some of its energy, so it becomes cooler. Particles move less, it becomes more dense, and it sinks. As it more dense air sinks and the hot air rises, it starts to create this swirling current. This is how warm spots in the ocean move to cold spots, like along the equator where the water heats, it flows up and creates currents. Convection currents are responsible for our weather across the planet. Okay, so here's an example in the daytime. The sun's shining. The land heats quickly. The air begins to, the particles move faster and it becomes less dense and it starts to rise. Okay, now the air is just not going to rise and there's going to be no air over the land. The cold air that's over this ocean or the lake comes in to replace it because it's more dense and it's down at the bottom. Then it gets here, it rises. This warm air, as it gets farther from the land, starts to cool off and it circulates back over to replace the air that came from the ocean, and it starts this convection current. And this is why if you're in the ocean and you're standing looking out, the wind during the daytime, the wind is always hitting you in the face. At night, the exact opposite thing happens. The water holds a lot of heat. It has something called a high specific heat. So it doesn't heat up very fast and it doesn't cool off very fast. So in the daytime, it doesn't heat up very fast. It stays at a pretty consistent temperature, but the land heats up quickly. At night, the land cools off quickly, but not the water. So the exact thing happens. The air over the water starts to warm, and it starts to rise, and the air over the land is cooling, so it creates a convection current in the opposite direction. This also happens in homes, okay? Sometimes you'll see these baseboard heaters along the bottom of a baseboard. As the air near this thing heats, it rises to the ceiling where it starts to cool, and then it sinks, and then it comes back, and it starts creating this convection current. So this air is expanding, and then as it gets farther away from the source of heat, the particles lose some of their energy. It's transferred to other things, and they get closer together, and the air becomes more dense, and it starts creating this swirling convection current. We also said that it's responsible for ocean currents. So you can see here that the water by the equator warms, and it becomes less dense, and it starts to rise. And it gets to the equator, and it becomes cooler, and it starts to condense, and it becomes more dense, and it sinks. So you have these swirling currents, which are convection currents of water in the ocean. On this map, we said that convection currents also cause the weather. So here you see that there's a band of deserts right here, and it goes, this is like the Mojave Desert in California, dry areas in Mexico, the Sahara Desert, Iran and Iraq, and this band of dry area across the Himalayas and the Tibetan Plain. And there's also another dry area right here, down through South America, parts of South America, and then Australia. And right in the middle where the equator is, okay, this is where the rainforests are. Well, what's happening here is this ocean water, okay, is this is where the most energy from the sun is coming. So what's happening is this is where the water is evaporating, and this is where it's rising. Well, as it rises, okay, right above the equator, as soon as it gets up a little bit and starts to begin to cool, okay, the water condenses and it just falls right back down there. And then the rest of the air current moves and it's lost its water. So as it moves, then it's over the deserts and the water has been drained out over here. The same thing with the convection current going south. So just north and south of the equator is where you have these dry areas. I want to take a quick look at this clip on convection currents. Okay, so we're going to take a look at a really good example of a convection current. They have two buckets of water. One of them is filled with hot water and one of them is filled with cold water. So the heat from the hot water is going to be heating one side of the aquarium, where those particles gain energy. They're going to move farther apart. They're going to become less dense, and they're going to be rising. Okay, where the water, the side of the aquarium over the cold water, is the particles are going to be slowing down. They're going to be becoming more dense, and they're going to sink. So it's going to create a swirling convection current. And this is how the weather works. Okay, if this was the land, okay, during the summer, and this is over the ocean, okay, the area over the land is going to be heating, and there's going to be rising, and then there's going to be an onshore breeze. So they've dropped in a drop of red food coloring on the hot water side and a drop of blue food coloring on the cold side. You can see immediately that the water on this side is rising, okay, because it's over a hot bucket of water here. So this water, the particles are moving faster, they're spreading apart, they're becoming less dense, and they're rising, okay. Now, the water on the hot side can't just rise and then there's no water there, okay. Something has to come in and replace the water that's going up. So it's going to pull in the water from the cold side, which is more dense. So you can see that it's already starting to move to the left. Okay, so if this was the summertime and this is you standing on the shore of the beach, the sand and the land is going to heat up really fast. Okay, the air over the land is going to be rising. If this is the air over the ocean, that air is going to be cooler and it's going to come in to replace the air that's rising over the land. And you're going to feel the wind. And this is what you usually feel at the beach when you stand looking out at the ocean, is that there's an onshore breeze. The air is going to be blowing inland. And at night, the exact opposite things happens. The water stays hot for a longer amount of time. And so it would be hot, and then the land cools down, so it circles the other way. This is a very good example of a convection current. This is a very good example of a convection current. The third transfer of heat is radiation. Radiation is transfer of heat by electromagnetic waves. Okay? Light and heat are both examples of radiant energy. Okay? Radiant energy really can be all the energy on the electromagnetic spectrum. Okay? Electromagnetic energy or radiant energy doesn't do any of it until it hits something. Okay? So it travels in waves, and some is absorbed when it hits an object. When it's absorbed, the object increases in energy. Usually we see this as an increase in temperature. Okay? Another example is microwaves. Okay? Over here, radiant energy does not do anything until it hits something, and then it's either absorbed or reflected. So you can think of this like in the wintertime when there's snow outside. A lot of the energy that's coming from the sun is reflected back, and that's why you can get such a sunburn, like if you're not wearing something over your face and you've been out in the snow for quite a while. Some of it is absorbed. So you can also see, like, if there's one thing poking through the snow, like a rock or a leaf or something, it's around that leaf where the snow will really start melting, or around a tree trunk. That's because thermal energy is hitting that darker object and it's being absorbed. So that one thing becomes warmer, where the rest of the snow is doing mostly reflection. I want to take a short look at this transfer of heat. Okay, so just a review of the three forms of heat transfer. Conduction is direct contact of the particles. So as the handle gains energy from the hot water, the particles are gaining energy here first, and they're moving the heat up the handle. The water is heating with this convection current. So it's rising as it gets to the surface. It cools a little bit and starts creating this swirling current. The burner with the pan not sitting on it is releasing this radiant energy as this heat moves up. Okay, so in this example, the fire is releasing this radiant energy. That's how it's getting to warm this person's hands. The poker near the fire, okay, the tip gets hot and it conducts up. As the heat rises from the fire, it creates a convection current. And here's another example of kind of combining the two pictures. You have radiant energy coming from the fire, swirling convection currents in the liquid, conduction of the handle. Okay, we're going to stop here and pick up with insulators and conductors next time. I hope you're having a great day, and we'll see you soon.